Our next speaker, thank you, speaker. Our next speaker is Wolfgang Thomas. He is working on automata theory logic, and is very well-known person, and will talk about solved infinite game in the Baire spaces. Welcome, Thomas.
Thomas, you're mute. Wolfgang, you're mute. On the bottom left corner.
Is it can you hear me?
Now we can hear you, yes.
Very good. Okay. So again, thank you and welcome to this talk. I was saying that I'm very glad to see so many friends and colleagues around, and also that it is a great honor to be part of this meeting commemorating Boaz Trakhtenbrot's 100th birthday. Let me spend a couple of minutes on Boaz from a personal perspective. He is, as you see here, a logician, a computer scientist, for me also a great educator. For the keyword of logic, I just recall a moving experience in CSL 1989. There was at Brno, there was a special session with the title 50 Years of Trakhtenbrot's Theorem. This is this theorem in logic, which, as everybody knows, tells us that validity of first-order formulas in finite models is undecidable. So he, in some sense, he prepared the subject of finite model theory, which came up later. And it was great to see this man in the audience of this special session, a very lively participant and contributing remarks. For the computer science keyword, I just want to recall that he, in a way different from Büchi, who always stayed logician, Trakhtenbrot had a broader perspective. He came from computer science into this subject, what we call today the Büchi-Trakhtenbrot theorem. He started, if you look at his book of the mid-60s, Theory of Finite Automata, with Krobrinsky, from real circuits, physical circuits, and very concrete problems like the control of railway crossings. And then he wanted a meta language, a high-level language in which one could express the behavior of finite automata. So this was his route to this theorem. And as a last point, I want to mention his great merits as an educator. Just one example. It is this book, the second book on finite automata, which came up in the mid-70s, 74 in the English edition. And in this book, you see in a polished and unified way the most difficult theorems which turned up in the years before on the infinite behavior of finite automata. There were two great theorems to be proven and very difficult, and I want to illustrate this on this slide. It has to do with the algorithmic solution of sequential conditions. Today we say the solution of infinite games. Church raised this problem, and in the realm of regular omega languages, a deterministic model of automaton was needed to control who wins a play or to control the run of a system. And Muller proposed such an automaton. We all know Muller automata today. This was in 1963, and he provided a proof. Equivalence to Büchi automata, the non-deterministic ones. And this proof was false. There was a mistake. And only 3 years later, McNaughton came up with the correct proof and showed this equivalence. Then McNaughton himself went to this church problem and in a technical report, which is not very well known, in 1965, he provided the proof of what we call today the Büchi-Landweber theorem, at the same time developing a very lucid treatment in the framework of infinite games as we do this today. But again, this proof of the Büchi-Landweber theorem of the solution of Church's problem was erroneous, false. Landweber found the mistake and later came up with the correct proof. And then in 1969, Büchi and Landweber proved their theorem. So the subject of infinite behavior of finite automata was difficult. The heroes made mistakes. And it was great to see this book then very shortly afterwards by Trakhtenbrot and Barzdin, where this was all put together in a coherent way. Now I want to stay with this subject in this talk and talk about infinite games. They came up, as we know, in descriptive set theory. And I want to mention 3 different versions of these games between 2 players, which build up in alternation infinite plays. In the first version, the items contributed by the players are bits or just letters from a finite alphabet. And so we use a set of bit sequences as a winning condition, say for the second player. When a play is in this set, then the second player wins the play. So the winning condition is in the Cantor space 2 to the omega if we deal with bits. The second version is rather the same, but the items of the 2 players are natural numbers. So this is then the winning condition for the second player is then a set of sequences of natural numbers. And one can say that this set is an element of the Baire space. If we look at n in an ordered as an ordinal, then it is in the space omega to the omega. If you look at the results of classical descriptive set theory, there's not a big difference between these 2 cases. The main results are concerned with determinacy, and determinacy holds, as we know from Martin's theorem, for the Borel sets, and the proofs in these 2 cases are rather identical, not essentially different. This is very different if we go to the algorithmic theory of infinite games, where determinacy is only part of the problem. We want more. We want strategies in a concrete way. And there we have this mentioned the Büchi-Landweber theorem for games over a finite alphabet. It says if we have such a game where the winning condition, say for the second player, is defined by a deterministic finite automaton, a Müller autom or a parity automaton, then determinacy holds. This is clear because when we use these automata for specification, then the winning condition is very low in the Borel hierarchy. But we can compute the winner, we can decide who wins, and a winning strategy for the winner can be constructed in the form, again, in finite state form, in form of a finite state transducer. And the question arises then, is there, again, for the algorithmic treatment, a corresponding result for games over the natural numbers? And I want to present such a result, which was obtained together with my last PhD student, Benedict Bridge, who I think is also in the audience, in this talk. And I put again this title of the Trakhtenbrot book to explain the structure of my talk. He has the 2 keywords, behavior and synthesis. And I will, in the first part, treat behavior, and I will introduce the automaton model, which is possible to, which I will use over infinite alphabets. And in the second part, I come to synthesis. Now, for automata on infinite alphabets, we have some proposals. There are lots of models in the literature, and I don't want to go through all of them here. I just put them on the slide. Many of them are motivated over finite words by applications in database theory. And so they are designed to recognize whether some values occur more than one time, etc. The model I want to use is different from these and is also very natural. And I wonder whether it has been studied before because it is so simple. We use automata over the input alphabet N. We have a finite set of control states and N as an additional memory. So a configuration of the automaton is a pair consisting of a control state and a natural number. And transitions go from configuration to configuration via input numbers. So these are the input letters. And for each pair of control states, PQ, we specify the admissible transitions by an MSO formula interpreted in the successor structure of the natural numbers. So for PQ, pair of control states, we have a formula phi PQ with 3 variables for natural numbers. And as you see above the red line here, transition PIMQJ is executable if in the natural numbers, the formula phi PQ holds with IMJ. This is the model, and you see the format below. We have an acceptance condition for finite words and for infinite words. For finite words, we only refer to the control states when we use the acceptance condition. So a configuration which is reached after a finite word is accepting if the control state of this configuration is accepting. And for the parity condition, which we use for infinite words, we color the control states by natural numbers, and we require that the maximal number occurring in a run, which occurs infinitely often, is even. So this is just standard if we look at these formats of transitions. So some remarks on these automata. If we use unary notation of natural numbers, then the ternary relations which are defined by these formulas, they are just the automatic ones. It is, however, dangerous to just say it automatic, because when you go to other alphabets, the model is not as well behaved as we have it here. We also introduced deterministic automata by requiring that these formulas are functional, P, phi, PQ, X, Z, Y in P, X, and Z, because we want that for each configuration and each input letter, there's exactly one new configuration where the automaton should go. This condition is decidable, so in some sense, it is a syntactic condition. One can avoid this uniqueness requirement by a different setup in which we replace formulas by automata, but I don't want to go into this detail. Some small examples. A very natural language of finite words which can be accepted is consists of the words where we increase by 1 when we go to the next letter. So from some number k to k plus l. This is easily programmed by such a computer, because in the transitions you can increase the memory content from configuration to a new configuration by 1 and control that the input letters agree to that. This is interesting, this example, because it is not covered by those finite state, by those automaton models, which I mentioned on the slide before, where the main emphasis is to detect the equality of values. But you can do this also with this model in some way. If you want the words where two occurrences of the same number arise, then one can do this by non-determinism. You just guess the first position where such a number occurs. You use the memory component to preserve the value and look whether sometime later this occurs as an input number. So that's easy. And of course, you can also use all this with infinite words. Their natural example is the set of unbounded infinite words. You use the Büchi condition or the parity condition, and you keep in the memory the maximal number seen so far. And when you increase this maximum, then you go to an accepting state. The closure properties of these automata are very much the same as for pushdown automata, and there is a connection to pushdown automata or pushdown systems. The nice thing about this model is that non-emptiness is decidable, also for the case of parity automata. We can look at variants of this model by using other logics for defining the transitions. A natural example would be Pressburger arithmetic, where we use first order logic with addition rather than monadic second order logic over the successor structure. But then you are too strong. You can simulate two counter automata or two register machines by coding a pair of numbers, two registers, m, n, by the number 2 to the m, 3 to the n, for instance. And then the +1 step in the first register means doubling, which can be expressed in Pressburger arithmetic. And the increase in the second register means tripling a number, the code, which is again expressible. So the non-emptiness is then undecidable. We have other versions which I don't want to treat in detail because time is short, and we want to finish this part on behavior by just mentioning how we look at transducers in this framework. There we have the same format as before, but the acceptance component is just replaced by some output component. And this is again a collection of formulas where for each configuration it is told which number is the output. So if Qn is the configuration, the output is K, if this formula psi Q with N and K is true. And again, we have that this is functional in Q and X, so we have a unique output. We use these automata or transducers to define winning strategies. And I now want to explain how this works. This is the second part of the talk about synthesis. And we give the theorem which we want to show. We consider Gale-Stewart games over the natural numbers, and the theorem says that for a Gale-Stewart game defined by such a deterministic parity n-MSO automaton, determinacy holds. This is as simple as before because we have a set of low Borel complexity. We can compute the winner, and the corresponding winning strategy can be constructed in the form of an n-MSO transducer. So in this sense, an analog of the Büchi-Landweber theorem is possible if we work over the Baire space and not over the Cantor space. Now for the proof, I give some remarks only. We use a notion which takes a different view of the natural numbers. In our model, in the automata and the transducers, the natural numbers are the atomic objects. But here we now look at their representation in terms of words, in unary notation, for instance. And what we do in one step is not change a number, but change letters. And then we are in the domain of push-down systems, push-down automata, and we look at formally at the tree of all words over some alphabet A, and use the standard tree structure with successor functions for each letter, one successor. If we have just two of these successors, then it's the binary tree as we know it from Rabin's tree theorem. And there are many definitions of prefix-recognizable graphs. We just take a logical one and say a graph VE with vertex set V and edge set E is prefix-recognizable if there are MSO formulas phi x and psi xy, which in this tree define the vertex set and the edge set. Very simple. And if we have different kinds of graphs where, for instance, we have two vertex sets corresponding to the two players and an edges set where, for instance, we go from V1 vertices to V2 edges and conversely, then this definition can be adapted also when we have an origin designated and or we have a coloring of vertices by natural numbers. The first main step in the proof is to transform automata as they are given for the specification of a game into a prefix-recognizable game graph where the vertices belong to one of the two players. This distinction is not made in the automaton. So a configuration of the automaton Qn has two representatives in these graphs by words. We take, as in pushdown systems, bottom, then the unary notation of a number, and then either the player 1 version of this state Q or the player 2 version of this state Q. And the transitions of the automaton are then transformed into edges in the graph by canceling the input number K, this is here, just looking at the changes of transitions and then using this representation as mentioned above. And the color of the vertices are then defined as the colors, if we use parity automata, in the automaton by inheriting them from the control states of the automaton. And then we have a result on parity games on game graphs, which for which we modify and use and reformulate results of Walukiewicz, Kashar, Vardi, Kupferman, Peterman, Vardi, and all taking all this together, we can show the following. If we have such a prefix recognizable parity game graph, say defined over a tree with the alphabet A, then the winning regions of the two players are MSO definable. This was done by Walukiewicz essentially, and hence by the decidability of the MSO theory of prefix recognizable graphs, they are decidable. This gives the decision who wins this play. Then there are, this is the more important point, MSO formulas that define, again, in this tree structure, the memoryless strategies for the two players in their respective winning regions. And to do this part B, we know we have to use some results on prefix recognizable graphs. The main point is the first, we simulate plays over prefix recognizable graphs by plays over pushdown graphs. And the difference is here that in a prefix recognizable graph, the out degree of a vertex may be infinite. And in a pushdown graph, it is finite, given by the number of pushdown rules of this pushdown system, each rule allowing one step to a next vertex. So this out degree is finite and bounded. And one can observe that this simulation is possible by dissolving or decomposing the an edge in the prefix recognizable graph by a sequence of edges in a pushdown graph. And then this graph is again prefix recognizable. And the main point is that memoryless strategies defined over vertices of this graph, so they are then words in the tree structure, which is used for this prefix recognizability, they can be described by a finite labeling of the tree, because there are only finitely pushdown rules in one step. And so a finitely labeled tree gives a strategy. And the winning strategy, say of player 2, correspond to a set of trees, which is regular. It can be defined by Rabin tree automata in a very strong version, which was developed among others by Moshe Vardi. We use here alternating two-way tree automata, which can walk up and down the tree. And they are then, they are equivalent to standard tree automata and to MSO formulas, and can recognize whether a strategy, such a label tree, is winning. And if such a set of trees is non-empty, then there is a winning strategy. And then we know that there is a regular tree, infinite tree in this language. And we can then see and work out that it is MSO definable and over this pushdown graph, and then also over the graph G. With some extra work, it is then possible to go back to the original framework of NMSO automata and find the corresponding transducer. This is technical work where we have to go back to the atomic objects, natural numbers instead of words. This finishes my sketch of the proof, and I just want to end with some issues or questions or problems. In this talk and also in our work, we did not at all address the issue of complexity. one can reduce complexity, but in a way which we did not work out. If we abolish automata, if we abolish MSO formulas and work as far as we can with automata, but this has to be done. A very interesting question arises, which comes from the weak closure properties of our automata. They are not logically well behaved. And the question is whether there is a logical formalism with closure under Boolean operations, for instance, that can take the place of these parity NMSO automata. It should be expressively incomparable to the automata, but be able to recognize the languages over the alphabet N as we use them here. I don't know how to do this. It is a question. And another point is about the topological complexity of these parity automata. They define languages in the Boolean closure of pi2 in the Borel hierarchy. They may define more special languages, open sets or closed sets or pi2 sets. And over finite alphabets, we know how to decide whether an automaton defines, in fact, a simpler set, an open set or a closed set. This is a theorem of Landweber. It should be possible also here for these automata to have a decision procedure, but we did not do this. And finally, there is a way to go beyond this Borel class Boolean closure of pi2. If you look at non-deterministic parity automata, you can recognize sets of Borel class sigma 3. An example is the condition that some number should occur infinitely often. In a non-deterministic parity automaton, you can do this. You can guess the first occurrence of such a number and then verify that it comes again and again. Deterministically, it is not possible, and it should be possible to introduce deterministic models of such automata with stronger acceptance conditions and go beyond the Boolean closure of pi2 and then show the analog of our theorem. So these are some ways to go, and you are invited to try. It would be nice to have some progress here. Let me finish now and say that I am very sad that I have to leave this meeting for most of the coming talks because I'm involved in another seminar among emeriti of my university, and I am co-organizer of this, and it was fixed much before this Trakhtenbrot 100 seminar, so I have obligations there, and if I don't listen to the coming talks, I ask for your for pardon. I have to excuse myself. Thank you very much.
Thank you, Wolfgang Thomas. Any questions, remark, comments? So I have a question. So you consider it synthesis for that specification is given by deterministic automata. And
Yeah.
when automata is non-deterministic, is it decidable, or you don't know, or is it open?
This is another open problem. We do not know how to decide whether a language accepted or recognized by a non-determinism can be done by a deterministic one. This is, well, it may be undecidable. You should look at the pushdown world and how it is there, and then try to copy the proof. But I don't know the answer.
Okay. Thank you very much. Any other question, remarks?